Cool. My name's Will. I'm at Protocol Labs. I'm going to sort of follow on to what Dropa was presenting over the last little bit and talk about a bit more specifics on some of the tools and patterns that we found effective in dealing with content address data, and then sort of a set of the directions that we're heading in thinking about a decentralized storage layer, so Filecoin in this specific case, and what that sort of path of decentralized data, structured data looks like as it interacts with that storage layer. Dropa went into hashes and what that means when you're actually talking about content address data. We're calling that SIDs, or content IDs. Within a lot of the IPFS protocol lab space, you'll see that as the term. One of the nice things to go to, if you just go to cid.ipfs.tech and put in a SID, it breaks it down and tells you what the sort of subcomponents of what that hash structure has in its internal representation. So it is, at its heart, a direct cryptographic hash, like SHA-256 or something like that. It looks a little different than just a SHA-256. We can break that down, and basically we've got a little bit of metadata that gives you information about which hash algorithm is being used and things of that nature that provide a bit more forward compatibility. So if you're using the CIDs rather than just a bare hash, you can change what hash algorithm you're using over time as you realize that MD5 is no longer secure, we need to upgrade. How do you do that? Well, it's nice to prefix, and so this is just the set of prefixes to let you do that upgrade. A lot of how we're moving bytes between different nodes is evolving towards an HTTP-like protocol. There's a spec for this that's getting called the trustless gateway specification, and so this is both how you pull stuff down from ipfs.io or dweb.link, but also from Filecoin nodes. So there's a spec on this within the IPFS specs, and really what it looks like is you ask for the root of a DAG, root of some structured data, and you get it back over HTTP in a car format. We've extended that so that you can also do it over libpnb and use the existing peer-to-peer transports, because that part doesn't matter so much, right? You can do it either way. But HTTP is a nice interaction with dApps and with web browsers, and just fraud with that. There's no reason to limit it to the sort of subset that is fully bought into libp. There's a couple interesting things here in what we're letting you, or what we're sort of setting as our standard and our interface for what we think makes sense for that request and responsive data here. The main thing that we ended up finding as sort of like a good baseline is this CAR format that we've had for a while. CAR stands for a content address archive. It looks a lot like tar. So if you've dealt with a tar file, you have a file name, and then you have the data of the file. This is, you have a hash, and then you have the block that hashes to that hash, and you just repeat that, and that's your CAR file. There's not too much magic. It's not too complex of a file format. But you can see that we're sort of taking a DAG, and we're just putting the blocks in order. And so that's what happens. You ask for the root, and you're going to get the blocks that compose that DAG that come there. We have a couple query parameters that you can use to specify how much you want. Do you want recursively everything within the structured data set, or do you just want the specific item that hashes to that 2 megabyte hash or something? So you can limit whether you care about sort of getting the stuff that is linked to, or you don't want to follow links and you just want the immediate object that you're asking for, and then do it in multiple requests if you've got a more complex subset of data that you care about, rather than wanting all. So that's a CAR file. And then the essential thing to think about as you get to a gateway specification, or what that data transfer is you ask for a hash, and you get back a CAR representation of that. And so when you think about sort of an IPFS node, if you've interacted with IPFS over the last decade, a lot of our data transfer initially was bit swap. And in bit swap, you'd ask for a hash, and you'd get back directly the thing that is that hash. And then you'd repeat. looks a lot like BitTorrent in sort of how it acts. And one of the things that's great about BitTorrent is as you've got a lot of peers that have that data, you can start to parallelize, right? You can be getting it from multiple of those peers at the same time, and so you can get an increased speed. The flip side, especially as you get into things like a blockchain data, where it's a long string of data, each block referencing the previous one, is that in something like BitSwap, you'd ask for the first block, and then you had to wait till you got it back to know what the next block to ask for was. And so you ended up pretty rate limited in pipelining that, because you had to ask for each one individually, and so you were waiting a full round trip of the network as you kept going. And we experimented with GraphSync, which is another protocol that's out there that allows you to do more complex selectors. So you can say things like, I want all of the blocks that meet this query, and then you could stream back all of that. The tooling and really sort of the way that you might think about that selector was always really unsatisfying. We didn't come up with a selector language. We tried things that looked closer to like JQ and how you might do selection of subsets of a JSON document. We ended up on something that's sort of like that, but a little bit more tailored to IPLD. And what we realized is really there's a couple sort of sub-limits that are most of what people care about and are much easier to understand. Either you want a direct block or you just want everything, or the two that were getting used almost all the time. That these more complex descriptions added a lot of complexity, were very hard to not make Turing complete, which was a problem because you could start to ask the other person in what you were selecting. As soon as it becomes data dependent, or as soon as it gets loops, very quickly you could potentially cause them to do a lot of work. And that got scary, because if I can make a query and you have to do a lot of work, and you're not giving me the data to cancel, I can cause types of denials of service. So we sort of backed away from that. And we find, I think, that we get most of the value out of something like this, where you ask for a very limited set of types of shapes, and then you get a car file back, and we can avoid most of the complexity. There's a CarV2 extension to cars that has tooling around it. It allows you to do random access reads over the car. So it puts an index that basically says where in this car file are the different hashes that are being interacted with. And so this, in things like a Filecoin node, allows you to have efficient access to data that's been packed into a large Filecoin field. You can seek to the end, you can get the index, and now you can know where in there individual files and data structures live, rather than having to download a larger deal of data. So that is getting some use within Filecoin, in particular, this type of index format and the CarV2 extension. If you need to go from just an archive, where you're doing a full export and restore of data, to instead wanting to be able to still have that data be sort of available for random access interaction, so reads of individual files within a data set, the CarV2 format is a reasonable way to get there. So let's talk about the write pipeline, which is the other part. Because as you start thinking about decentralized storage, you've got a read pipeline and you've got a write pipeline, right? So reads, I think our hope is that you can use things like IPFS gateways, and then eventually the browsers, the dApps and the clients have, will get upgraded to natively take that sort of interaction where you're going to a gateway and translate it into a full IPFS pipeline. So the hope is that for most dApp developers on your read pipeline, you can prototype and you can start now by just using an IPFS gateway, and everything works. And then as browser tech and users upgrade over time, you'll get the benefit of additional resilience and of being able to switch which gateways, so that the requests end up going to the native hosts that are hosting that data in addition to the gateway that you've chosen. There's reasons to, as you end up with performance SLAs and things of this nature, you can choose the specific gateway URL to one where you've got an SLA with. So you can start to say, okay, hey, Web3 storage is willing to provide this gateway that actually gives me some SLA that it'll always return to my users in 500 milliseconds, or Saturn does this. So you can go to these accelerated versions, And the point is that that's just a URL switch. So hopefully that's not a big deal on your dApp. But either way, for users whose browsers are IPFS enabled through an extension or through things like Brave integration, they'll be able to get the data from IPFS through content routing without having to use this necessarily. So that's the read side. On the write side, for how do I get this data pushed out to some decentralized storage layer, I can take you through sort of a journey of like what's safe and what's doable now, and then the directions that we're heading. So right now there's a set of services that you will probably make a relationship with one of them to allow your users to store data to a decentralized storage. Initially, those were pinning services like Pinata and so forth, where you become a client of them, and then you get an API key and you can use that to store your data so that it stays available. Today, there's additional ones like Web3 Storage that have a similar model. They provide an HTTP API where you take your content address data and you can push it to have your users directly push it to their server. They'll bundle it up, they'll keep it available, and they'll get it eventually into things like Files and IPFS. Reasonably simple JavaScript APIs or Go APIs to integrate with whatever your front end is that's generating this data. The thing that's getting worked on in sort of the next iteration of this is starting to exist in things like Lighthouse.storage. What they're doing is they take your file or object and they let you generate directly the proof of that data. So even though your data isn't a file point deal or something of that nature, you can take a hash over the full image or the full video file. So if you've got your 2 meg image or your 4 meg image, in addition to doing the chunking and the IPFS transformation that Jerome talked about, you may want to be able to say, those blocks, when I think about them as a 4 megabytes of contiguous set of data in a car file, I want to know that I've got that car file available on this decentralized storage layer. It's not that I want the root of the file and I don't know which of the subdags, which of the blocks and the subset of blocks are there. I want to actually know that I've got this car file available for people to pull that down. I want that whole, it's a collection of hashes. So you can hash over that car file, and and we're calling these sub-pieces within the file point terminology. And we can begin to aggregate and give you a Merkle proof that an overall file point deal that eventually gets made includes this sub-piece of your 4 meg hash. And so when you use something like Lighthouse, which has pretty much the same API as Web3 Storage right now, the benefit is that what they give you is that Merkle proof, so that you can see that your car file that you uploaded actually has made it into a deal. And subsequently on renewals, you can make sure that you've still got the right replication and know which storage providers have your sub-piece of your actual content. So rather than having to think about this aggregation of data up at a file point deal size, which is just this arbitrary, relatively large size, we can pull that down to the scope of data that users actually are caring about of their image or their users' data DAG. This is still, you're choosing some provider, but you're trusting them a bit less because you're getting a cryptographic proof that it's ended up in this decentralized storage layer. As you get there, to that slightly lower trust, where you're just trusting on availability and a pricing agreement, you can then move to a full market where you've got your object and you've got a bid, and whoever is able to prove to you that they've got it into a final storage object is then able to get the result of that balance in essence. And so you stop having to trust an individual aggregator, and instead you just have your car file, and once someone's able to prove that they've got it onto storage, you're able to pay them or release the payment and have that sort of work in a fully permissionless way. So that's sort of the coming iteration as we get tooling finished around this sub-pieces. This layer is also called PodSci, Proof of Data Segment Index, and is starting to get made already through both Web3 Storage and Lighthouse. So this is the direction we're heading for how you get to a permissionless write layer for objects within the contract address. I think that's the basics of what I was after. I won't hold you guys from lunch for too much more.